welcome everyone. So in this video, I'm going to talk about oligopoly. Basically, I'm going to talk about the Cournot oligopoly, then I'll show like the extension to the N-firm Cournot, then I'll think about Bertrand, and then I'll do an extension to the hoteling oligopoly, which makes use of kind of some Bertrand ideas, like price choosing ideas, but also thinking in terms of particular product differentiation dimension, like some characteristic or geographical space. So if you like the video, go ahead, leave a comment. That could really help. I mean, my whole goal of putting my stuff here is to be able to reach and help people. I was just thinking about this before I was making the video. The reason why I started making videos is because I learned my linear algebra from Gilbert Strang, who had made videos back probably before most of my students were born. And so this is the new edition, I guess, and Gilbert Strang's still there making videos. So he's at MIT. I think there's a course from 2011 or something like that. That's not the one that I was using. So I was using the course from 2000 or something like that. And anyhow, so they're still there, and that was before people had good content where you could kind of self-teach. And so anyhow, since I benefited so much, I try to have my stuff out to help people as well. Also, just because the university system for making lectures on Zoom, they get deleted if you don't host them somewhere. And so I was just having control over where the videos are and not doing something that then gets lost forever. As evidently, maybe I don't know, somebody's probably saved Gilbert's videos. I hope so. Actually, I probably have them somewhere on some old hard drivers, something or other. Anyway, so without further ado, here we'll talk about oligopoly. I've called this the Oligopoly Interlude. And so in the middle of the course, this is sort of piloting a new lecture. I'll have some other ones, like entrepreneurship of I don't know, applications of blockchain and information goods and apps and those sorts of things. So I've got some additional, this is for the economics of entrepreneurship course, but that's why it's handwritten, because I'm just sort of piloting this one. And if I like the lecture, if I like the video, then I'll make it onto the nice slides and everything. But anyway, so what we're thinking about with Cournot is we're thinking about a quantity choosing firm. So we've got an identical product. Firm 1 is going to produce Q1, just one, this firm 1's quantity. Firm 2 is producing Q2, that's firm 2's quantity. The market has just whatever is the amount that's being produced by the two firms, or if there's multiple firms, just sums up to the total market quantity. Then I'll write down inverse demand. I'll write it down linear, so it's going to be price is equal to, this is the vertical intercept minus a slope of 1, and then Q. The slope could be anything, it doesn't need to be 1, and also the functional form could be varied as well. It doesn't need to be linear demand. There's some interesting things that happen if you have nonlinear demand, but it just adds a level of complexity we don't need at this point. Okay, so let's just take as an example, the inverse demand is 100 minus Q. And so Q is, of course, comprised of the quantity from firm 1 and firm 2. Good. So then we'll just distribute out this minus, the slope of 1 to both of these quantities. If, for instance, this is like a minus 2, then it would be 100 minus 2Q1 minus 2Q2. Or actually, if the two firms' output were not viewed by the market the same way, this could be like a 2 and this could be a 1 or something like that. Remember, the way we think about the demand is that there's only a certain amount of output that this market will bear. So Q at most could be A. Otherwise, the price, that's where the price is 0. Otherwise, the price would be negative, which doesn't work. Well, is awesome for consumers, but doesn't work for the firm. And so we think about right now firm 1 and firm 2's outputs entering the same way into demand, but it could be that there is a different penalty to the total price coming from firm 1 and firm 2. So if this was minus 2Q1, then the maximal amount of Q1 of firm 1's output you could possibly have would be 50. So it'd have twice the penalty to the overall quantity that would be tolerated by consumers. Anyway, that's the interpretation of different slopes. So let's not worry about that any further than what I just said. Okay, so we're assuming firms are facing costs that are possibly identical. I'd just give a total cost function. For here, we'll just use constant average cost, constant total cost. And so it's just marginal cost of 10 for each firm, though this could be a different functional form. What do? You just write out total revenue minus total cost. You'll take your first order condition, and then the equations just work out nicely. So just for our purposes, it's nice just having a constant marginal cost, and that works out for the formula for equilibrium quantities we'll develop at the end. Anyway, so each firm's going to choose its output, taking the rival output as given. So thinking that the rivals are going to produce some constant. That's the assumption for Cournot, so it's static. So the idea is we're just going to choose our output, thinking that our rival has chosen some value, some numerical value. This is like some static amount. There's no reaction right now at this level. So we'll build in a reaction into a reaction of firm. We'll build in firm 1's reaction, understanding of firm 2's reaction to firm 1's choice when we make the Stackelberg model. I've got a separate video for that. That won't be in this one. And then firm 2's choice would be a function. Here, firm 2's choice is just a number. So anyway, then what we'll do is I'll just kind of distribute the quantity and then clean up by collecting like terms. So before I take the derivative, it's 90q1 minus q1 squared minus q2 q1. When I take the derivative with respect to the choice variable, I'll get d pi dq1, or 90 minus 2q1 minus q2. And then I'll solve for q1. And this gives me firm 1's reaction as a function of firm 2's choice. I always like cleaning up the fraction, and so making this 45 minus 1 half q2 rather than writing it as 90 minus q, all of that over 2. And the reason why is when we solve the system of equations, it solves some of the issues of where you might forget to multiply or distribute the 2 by everything when you're taking it out of the denominator. So you'll see that everyone's got their own preference for how they want to solve reaction curves, but I think it's slick. It's way better to do it this way if whatever is this value, if it's divisible by 2, it's even, or if it's nicely divisible by 2, meaning something that's not even but not horrible to work with. So for instance, I'd classify like something that's going to leave a nice fraction, like a nice decimal, like 21.5 would be fine, but some nasty decimal wouldn't, and so then I'd probably leave it as a fraction. But anyway, so that's just thinking about in terms of what's in front of us when we have to solve the system of equations. So each firm is going to choose its rival function, its choice as a function of its rival's choice. So here's the best response function for firm 1 and for firm 2. This game was symmetric. They have the same costs. We already established that the demand curve, the demand views these two quantities the same. The market views the product as interchangeable between firm 1's output and firm 2's output. And so we can just switch the labels to get the reaction curve for firm 2 as a function of firm 1's choice. If you don't want to just do that, like everybody at least once should set up the problem from firm 2's perspective and then verify that that's true. So I've just got that work right there. Good. Now we've got our collection of best response functions, and we're solving the system of equations. So basically what I'm going to do is I've got firm 1's choice as a function of firm 2's choice, and so I'm going to replace Q2 in firm 1's best response function with 45 minus 1 half Q1, which was firm 2's reaction to firm 1's choice. That gives me one equation, one unknown, and then just solving algebraically. Cool, we get a quantity of 30. Here's the graph of the best response function. Sometimes that's helpful to see graphically, these best response functions. This is, we have Q2 is firm 2's choice. Q1 is firm 1's choice. BR2 is firm 2's best response to firm 1's choice. BR1 is firm 1's best response to firm 2's choice. 30-30 is that's just the Cournot equilibrium that we find here from solving the system of response curves. And then what's this 90? Well, remember the market would maximally handle 100 units, but firms each had a cost of 10. And so the most that any firm would bring to the market would be 90. But if firm 1 if Q1, firm 1 set a quantity of 90, then firm 2's best response is 0. If firm 2 sets a quantity of 90, firm 1's best response is 0. Remember, this is 0, so this is like where firm 1 sets a quantity of 0 and firm 2 sets a quantity of 90. And then what's this 45? Oh, those are corresponding to the monopoly situations. And so if it's the case, so we're going along here, we're looking at firm 2's best response. So firm 2, Q2 is increasing as Q1 falls. And we go down here, all of a sudden, if Q1 goes to 0, firm 2's best response to 0, their monopoly output is 45. And then firm 1's best response here, Q1 is increasing. So we go to the right, Q1 is increasing, and down to the right means Q2 is decreasing. Here's firm 1's monopoly output when firm 2 sets a quantity of 0. And so you could get the monopoly output. That was just like A minus C over 2. So that's going to be 100 minus 10 is 90, over 2 is our 45. That's where that came from. But, so I'm breaking into the video, obviously, and the reason why I wanted to do that, besides just explaining this a little bit better than I kind of did the first time, I want to show my puppy study break. So here is puppy study break. And what I was doing, look at this face. This face. Do you know what puppy study break did? Here I am, this is my knee. I was sitting here, I was playing Madden 22, and eating popcorn. And puppy study break realized that I was eating popcorn. And then what did puppy study break want? She wanted the popcorn. So anyway. Yeah, and then here's the residual inverse demand. So this argument is just, or what I'm doing right here is I'm just saying, hey, look, firm 2 is producing some amount. Firm 1 is taking that choice as given. If firm 1 knows that firm 2 is bringing 30 units to the market, now because the maximal amount that this market would bear would have been 90, we know that firm 1's not going to be able to put in any more than, for instance, 60, but that's not actually what they want. What they want to do is they want to bring in whatever is their optimal amount, conditional on the residual demand, whatever is like the remaining appetite of the market for this good. So here's that comment. Since the market demand is price is equal to 100 minus Q, once firm 2 sets Q equals 30, the market price is 70, and then any quantity, any positive quantity is going to cause the market quantity to be larger than 30 and the market price to fall below 70, right? So firm 1 is now being aware of the penalty in terms of the price that's going to be shared by both firms. And so what it's going to do is it's going to look to see, all right, if this is the residual demand, where's my residual marginal revenue curve? Where does that cross marginal cost? Oh, it's right here. So we want the total market quantity to be 60, looking at just the residual demand as though this was the vertical axis. From this point here, firm 1 wants to produce 30. And so that's the other way to reason to it. I'm not going to do that with equations. I just wanted to kind of show kind of a little bit of what's happening behind the scenes with Cournot. But anyway, the residual solving for where the residual marginal revenue cross marginal cost yields the same quantity of 30 that firm 1's going to want to bring to the market. We can calculate our Cournot profits. So it's just going to be, well, we've got the price minus the total market quantity. That gives us a price of 40. So this is 40 minus the marginal cost, which was 10. So it's going to be 30 squared. Okay. And same thing for the other firm because it was symmetric. Here's the extension. This is now looking at the n firm Cournot. So it's like, what if the market quantity is coming from n other firms, right? We can write out profit for firm 1 as a function of everybody else's numerical choice. So this is firm 1's revenue minus firm 1's cost. And I've just kind of cleaned up. Remember, you're going to have you're going to have like a minus A distributed to like Q1 here when you replace the demand curve. This demand curve is going to be price is equal to A minus Q1 minus Q2 all the way up to Qn. And so I'm just going to collect like terms here and write this as A minus C Q1, and then here's the Q1 squared term, and then here's going to be the expansion of all those Q1s times Q2 through N, right? All right, so when you take the first order condition and solve, you're going to have like the A minus C term that's familiar from before, 2 minus Q1, that was from the square, and then you're going to have Q2 all the way up to Qn. And then if the firms are identical, and we made that assumption, then we can just say, oh, all these quantities are the same in equilibrium when we have the star there, meaning this is the equilibrium quantity. So then I can just clean this up real nicely. I'm going to have A minus C minus N plus 1 contributions of Q star in the market, and then solving for Q star, it's just going to be A minus C over N plus 1. That's exactly what we just had. It was like 100 minus 10, which was 90, divided by 2 plus 1 divided by 3. So that was our 100 minus 10 divided by 3, or our 30 for our 2 firm Cournot. The total market quantity is just going to be, well, N times that Q star that we just found there. And the market price is going to be A plus Cn N plus 1. You would never do this. The way that you find the market price is you just like subtract the quantity, you go to the demand curve and deduct the market quantity from the intercept, and then you have the price. But if you wanted to find the formula for the price, you could do that. And then let's see, question about like where the plus term comes from. So you're going to have like an A minus this stuff right here. So you have A minus this because this is your Q. And so you need to get common denominator. So it's going to be an A times the quantity N plus 1 over N plus 1. And then you're going to have an A N plus A, and then minus an AN and minus a plus Cn. So that's where you're going to get the A plus Cn from. Your An minus An cancel. It's easy enough to do. So, but that's where that came from. All right, so then I'll talk about Bertrand. So the idea with Bertrand is we've got fierce price competition, and we've got the result where if firm 1 sets a price below firm 2, then no one's going to buy from firm 2. If firm 1 sets a higher price, then no one's going to buy from firm 1. And so in equilibrium, they set the same price, equal the marginal cost, and then they split the market evenly. So here they'll set the same quantity. And so the quantity is just going to be 100 minus P divided by 2 because we had two firms. If marginal cost was 10, then the equilibrium price would be 10. And that's our Bertrand equilibrium. There's a Bertrand paradox because here with identical products Bertrand, we've got two firms and we've got the price equals marginal cost outcome. And the paradox is like usually we expect that you have to have many sellers to be able to get that result. Here you can just get it with two. It's because we have identical products and because they're using this sort of fierce price undercutting in this market. Here's just a further development. Suppose we had a different issue where we no longer had the same. So first I'll do the dynamics, then I'll think about no longer having the same price. So suppose marginal cost was 10. The equilibrium price we know is 10. What if the price was 10.50? Then what happens? Oh, one of the firms is going to want to capture the market with 10.49, and then the other firm is going to capture it back with 10.48, and so on and so forth, all the way down to a price of 10. If marginal cost equals 10 and marginal cost of the other firm is 10.25, what happens? Oh, firm 1 is going to set a price of 10.24, capture the entire market. Firm 2 is going to set a price of 10.25, and that's just what they're going to do. They'll produce zero. If there are capacity constraints, though, then firm 2 could serve whoever firm 1 can't at a price of 10.25. Even so, firm 1 wouldn't want to price anything other than 10.24 because they don't need to. They're not facing competitive pressure below the price of 10.25 because firm 2 can't do that because their costs are too high. And so if you have a situation where firm 1 isn't able to serve all the customers, then firm 2 could come back in. But otherwise, they would be out of the market. All right, so the last extension is thinking about the hoteling duopoly. So this is price competition with differentiated products. So for instance, suppose we had a mile-long beach with customers located throughout. Each values the good at $V. It has a location X and utility given by the transaction, or given, assuming transaction costs of T, which is like the nuisance or bother that they incur either walking to, along the beach to the other vendor away from their location, or if we're thinking about this not as a beach but as some like dimension of taste, then it's buying something that doesn't match their preferences perfectly. So here is their utility. This is the utility for a person at position X. So it's going to be this V minus the price they pay minus T times the transaction cost that they're going to incur. If they buy from firm 1, here's what happens if they buy from firm 2. If they don't buy, the utility is just 0. So for example, the numerical version, suppose the value is 8, suppose the transaction cost is 2. So then if they are able to buy, if they were given the good for free, and they're from a seller that's exactly where they're located, their utility would be 8, right? This would be 0, and then this would be 0. Suppose not. Suppose they actually have to buy for a positive price. Well, then it's going to be 8 less whatever the price is, and then less however far they went times 2, because they'll incur a transaction cost of 2 for each unit that they're moving, or for each incremental move away. All right, so then what I've done is I've found which consumer is indifferent between buying from firm 1 and firm 2, assuming that they're going to buy from whichever is closest. So I just do that by taking this line and setting it equal to this one. So when this is equal, the X that makes these two, the utility from firm 1 and utility from firm 2 equal, gives us the position of being indifferent between the two sellers. Just algebraically solving, I get a position of P2 minus P1 plus 2 over 4. If there's 1,000 such customers, then each firm's quantity demanded, assuming each buys from whoever's closest, is going to be 1,000 times this right here. So this is going to be the person in the middle. We're just bisecting or dividing up the unit interval. And so if there's 1,000 such customers, then and they buy from whoever's closest, then 1,000 times this many are closest to firm 1, and 1,000 minus this many is, or 1,000 times this, or 1,000 times 1 minus this many is closest to the other firm. So What does this end up being? It's 1,000 times this stuff. 1,000 divided by 4 is 250, and then this was just the numerator, and then you could find whatever are the prices to make that happen. And then similarly for this other side. All right, so if the firm's costs are, for instance, 4Q1, and so that the marginal cost is 4, then the profits can be calculated by just revenue minus the cost here. We have the markup as being the price of firm 1 minus 4. The quantity we had from up here, so this is 250 times this stuff. All right, so this gives us an expression for firm 1's profit. We just take a derivative with respect to the price, and that'll allow us, after cleaning up, to get an expression for firm 1's optimal price. It's right here. P2 over 2 plus 3 is equal to firm 1's price. By symmetry, the two firms are identical, so then firm 2's price is going to be just P2 is equal to P1 over 2 plus 3. We can find the equilibrium because these are actually reaction curves. As you're staring at this, this is firm 1's price as a function of firm 2's price, and this is firm 2's price as a function of firm 1's price. So let's just substitute one into the other. And if we do that and then solve, sure enough, we're able to get our equilibrium prices, P star 1 and P star 2, which is just going to be 6. With those prices, that's enough for us to find the quantity buying from each firm. And because this game was symmetric, it turns out being, I made this with dollars. This should be 500 people, and this is 500 people. Forget about that dollar sign, right? All right, so, and then profits are just going to be, we'll go back up to firm 1's profit expression. It was 250 times price minus 4, which is cost. So it's going to be 250 times 2 is 500 times this stuff here, it's just 2. Is 1,000. So $1,000 to each for profits. And then the last thing was just kind of thinking about how this would look in terms of overall product space. I don't know. So here's like the mile-long beach. Here's the price of good 1. Here's the price of good 2. The line is the full price from buying from firm 1, including the transaction cost right here. And this line is the full cost of buying from firm 2, including the transaction cost, right? On the assumption that here's whatever is the price. The transaction cost was like 2 or whatever when you went the full step from 0 to 1. And so this is just saying, basically, it's graphically showing, oh look, here's whatever was the monetary price, but the actual price incurs me like walking across the beach. So by the time it's all said and done, I'm paying 6 for the unit or for the good that I've bought, but I'm also paying 2 with this like nuisance cost for having to walk across the beach from point 0 to point 1. So it's going to be 6 plus 2 to 8 for the full price. And then if I'm located down here, buy firm 2, good if firm 2 is going to sell to me because I can buy it for $5. Otherwise, I'm going to still pay $5 and lose another $2 from having to walk all the way down to the other end, right? So that's just the idea there. Here was the example. So the initial prices the price of the good was $6 for good 1, $2 or $5 for good for firm 2. Transaction cost was 2, and the point is the consumer at point 0 pays $6 to buy from firm 1 with no transaction cost. Consumer at point 0 pays $5 to get the good from firm 2, but also incurs a $2 transaction cost for a full price of 7. Anyone between 0 and X is going to buy from firm 1. Anyone between X and 1 buys from firm 2. And as a result, we could get these equations. But anyway, just kind of, this is more conceptually like what's happening. 25% of the market's going to buy from firm 1, and 25% or 75% is going to buy from good 2, based on these prices, based on these locations, and based on these transaction costs. So anyway, I want to do that kind of quick so the video's not too long. Hopefully you enjoy the video. If you do, like. If you don't like it, as what, dislike or whatever. I don't know. Leave a comment. Tell me what you're doing over the weekend, had for breakfast. All those things, I guess, help YouTube or whatever. Anyway,